Hello and welcome to this look at radical substitution with a focus on further substitutions, how they might be achieved, and some limitations to the mechanism when you're trying to make a specific substituted product. So let's review the mechanism first of all. We'll start by looking at chlorination of methane, which is the easiest and simplest version. So it involves homolytic breaking of covalent bonds, in this case between chlorine atoms in Cl2. So the overall reaction equation gives you a monosubstituted product, CH3Cl, and HCl as a side product. So simply all that's happened is one of the chlorines in Cl2 has replaced one of the hydrogens in CH4. So to achieve this, you need ultraviolet light to instigate or initiate the breaking of covalent bonds, the homolytic fission. And if we use excess methane, what this does is it starts to control further substitutions, which I'll talk about a little bit later. So obviously you start with the initiation using ultraviolet light to homolytically break the bond between the two chlorine atoms in Cl2, which gives you two chlorine radicals. So one of these approaches a CH4 molecule and reacts with it to produce CH3 dot. Now you put the dot next to the carbon because the carbon carries the unpaired electron in that radical. You make a hydrogen chloride side product. And now the methyl radical, as we call it, goes and reacts with a fresh chlorine molecule to make our monosubstituted product and a new chlorine radical. So these two steps in that order are called propagation steps. So there's ways in which this can finish. In other words, the radicals can come together to make molecules. So one possibility is a methyl radical and a chlorine radical. Now there's excess methane, as we said, set up at the beginning. So that would be called a major termination step. There's two other possibilities. There's also the methyl radical coming together with another one to make CH3CH3. So just to clarify, in the initiation step, radicals are made, and then propagation steps, radicals attack a molecule to make a new radical, another molecule. And in the termination steps, two radicals, they can be the same as each other, or two different types, combine to make a molecule and the reaction stops. So like I said, the position of the dot is very important. It must be placed next to the atom which actually has the unpaired electron, which is in this case carbon. So then we've got the final possibility of termination, which is two chlorine radicals come together to make Cl2. So this will be a minor termination step. There's not very much of this happening because most of the chlorine radicals will have been used up by this stage because we've set up the reaction mixture at the start with more methane and less chlorine. So we can actually manipulate the various proportions of the reactants to end up with different products. So if we look at the different overall reaction equations that are possible, so what you're noticing here is you're getting further substitutions. In other words, instead of just CH3Cl, you make CH2Cl2. And each subsequent product reacts with a new chlorine molecule to make another substituted product. And what's happening in each case is there's more hydrogens taken off and more chlorines substituted on. So if you had excess chlorine, you would end up with these multiple substitutions. So to maximize the yield of one of the intermediate substituted products, we might use more methane so that the chlorine runs out first. If, however, we might want complete substitution, in other words, all the hydrogens which substituted for chlorines, we might put more chlorine in our reaction mixture to encourage that to happen. Now the problems with further substitutions are if you're trying to make one specific thing. So let's imagine we wanted to make CH3Cl and nothing else. What will happen is if you have too much chlorine, you'll start to get further substitutions like we said. So it doesn't stop there. We'll get all these products as well. So what actually happens is you end up getting a mixture of all the different possible substitutions, some partial substitutions and some complete substitutions. In other words, partial means some of the hydrogens have been replaced and complete means all of the hydrogens have been replaced. So let's have a look at an exam question where they might ask about this. So under suitable conditions, butane C4H10 reacts with chlorine by radical substitution. A mixture of organic compounds is formed, including C4H9Cl. Now that's a monosubstituted product because only one chlorine atom is substituted onto the butane molecule. They don't want you to bother with the termination. It's only 2 stages, and they want molecular formulae, so that avoids having to work out where on the carbon chain substitution has happened. So it reacts with chlorine, which tells you that the first stage is going to be initiation with Cl2 turning into 2 chlorine radicals. Obviously, like we've said before, the conditions are UV light. So doing the equivalent propagation steps, you start with a chlorine radical reacting with the butane to make C4H9, a butyl radical, and HCl, and the butyl radical in the second step reacts with a new chlorine molecule to make C4H9Cl, which is our product, and Cl dot, which is our chlorine radical. Then it says organic compound D is formed by the substitution of all the hydrogen atoms in butane by chlorine atoms. So taking the butane molecule, what we need to imagine is that all these hydrogens are being replaced by chlorine. So we can construct something like this. Now it's not balanced yet, obviously, because you need to think about how many chlorine molecules you need and how many HCl's you're going to get. So you'll need enough chlorine atoms on the left to provide 10 chlorine atoms for C4Cl10 and enough for 10 HCl's. So moving it over a little bit to make some space, that means we put the number 10 in as our balancing numbers on the left and the right. So the second exam question we're going to have a look at, where it says state 2 limitations of using radical substitution in organic synthesis. Now organic synthesis means basically making a specific product, one thing. So if we get multiple undesired substitutions, i.e. a mixture of products, that's going to be a limitation to this technique. Also, you could get a range of substitutions at different positions on the carbon chain, maybe carbon 1, carbon 2, carbon 3, for example. So if we have a quick check of the mark scheme, you can see the kind of things that we can get our marks for. And it's quite flexible if you look at the guidance on the right-hand side, the different ways in which you can get those marks. So our third exam question is in 2 parts, so let's do part A to begin with. So in alkane A, which is shown below, they say it reacts with bromine in a radical substitution reaction. So they're focusing on the monosubstitution idea. What this means is only one hydrogen atom is replaced with a bromine. So if we take the hydrogens on those methyl groups, and if you replace one of the hydrogens with a bromine, you'd get the same compound, 1-bromomethylpropane, which looks like that. So it doesn't matter where the bromine is, whether it's on the top methyl, the left-hand side one, or the bottom one, it's still going to be 1-bromomethylpropane. If we were to replace the hydrogen on its own, for example, that would lead to 2-bromomethylpropane. So what they want is those 2 isomers, like that. So if we check the mark scheme, that's exactly what they've got. And an important marking principle from OCR is going to be allow any combination of skeletal or structural or displayed, as long as it's unambiguous. Unambiguous meaning that there's no way it could be confused with anything else. So part B of our third exam question, it says with excess bromine, further substitution takes place. So they want an equation for the reaction of alkane A with excess bromine to produce 1,3-dibromo-2-methylpropane. So let's start with reminding ourselves what alkane A was, and then we can have a look at what the compound we want to make actually looks like. So let's think about this. We need a bromine molecule to provide these 2 atoms, the 2 bromines there. But also remembering that we've got 2 hydrogens that have been replaced. So we need 2 further bromine atoms. So therefore we put a 2Br2 on the left-hand side to give us the 4 bromine atoms that are now distributed between the 2 products. That's what our equation will look like using structures for the organic compounds. And with a quick check of the mark scheme, again, that's exactly what we did. And the same idea will apply this time round. Okay, thanks for listening. I hope this has been useful. Until next time, see you soon.